Okay, so let's talk about the image of a linear map. Okay, so the definition of the image is just the same thing, exactly the same thing as the image of any function. So you've got a function. It happens in our case that it's a linear map from a set E to, well, let's call the codomain F. So the image is denoted em of F. It corresponds to all the values that are reached by all elements of E. So you can also use this notation, okay? The image by F of the whole linear space E. Okay, so the image of F equals to F of E is all the elements of of the codomain, such that there exists some X in the domain with all elements Y in the codomain, such that there exists X in the domain, such that Y is equal to F of X. Okay, and another way to write that is the set of all F of X's for all X's in E. Okay, so it's just a very typical way to describe the image of a function. It just happens that in our case it's a linear map, but to define the image it doesn't change. All right, so first results, the image is a linear subspace of F. So this should be very easy to prove. So let's try this. So we want to prove that the image of F is a linear subspace of F. Sorry, of the vector space big F. Okay, so as usual, you have to prove two things. First thing, it's not empty. Well, yeah, it's not empty, so very easily, usually you try the zero item, and we already know that 0f belongs to the image of F. How do we know that? Because we know that the image by function f of the zero element of E, we know that by linearity, that was one of the previous propositions, it's equal to 0f. So there exists an item in E, which happens to be 0e, such that f of 0e is equal to the 0 of f. Okay, so 0f belongs to the image of f. Okay, first thing. Next thing, the usual linearity property. We say, let's take y1 and y2 that belong to the image of f. Let's take lambda that belongs to R. Do we have that lambda y1 plus y2 belongs to the image of f? Okay, that's the question. I mean, if it's okay, then we have a linear space. So let's first translate what it means to have y1 and y2 in the image of f. y1 belongs to m of f. It means that there exists x in E such that, let's call that even x1, such that f of x1 is equal to y1. Okay. Y2 belongs to the image of f. Very similarly, it just says that there exists some x2 in E such that f of x2 equals to y2. Okay, so now what about that part? So do we have that lambda y1 plus y2 belongs to the image of f? It means, can we find some x can we find x that belongs to E such that f of x is equal to that lambda y1 plus y2? Okay, if we can, then it means it belongs to the image of f. So very easily we can say that lambda y1 plus y2 is actually equal to lambda times f of x1, because we said y1 was equal to f of x1 plus f of x2, and this is where we can use the linearity of the map f. So as f is linear, we know that we can put all these together. We get that this is equal to f of lambda x1 plus x2. Okay, usually we use that the other way around. Usually we say that, well, we have this, so by linearity it means that. Okay, we have that f of lambda x1 plus x2 is equal to the linear combination of the images, but it works both ways because it's an equality. So that's it. What does that mean? It means that there exists x that belong to E, and that x is actually equal to lambda x1 plus x2, and as E is a linear space, lambda x1 plus x2 is a linear space, so x belongs to E, such that f of x is equal to lambda y1 plus y2. Okay, hence lambda y1 plus y2 belongs to the image of f. And finally, we can conclude that image of f is a linear subspace of f.